So now that we have some basic vocabulary about sequences, I want to introduce some key concepts here. The first one that we're going to talk about is the idea of a bounded sequence. We'll say that a sequence is bounded if you can find a real number capital M so that the absolute value of a sub n is less than or equal to capital M for all indices n. So we saw that in our discussion of absolute value, that saying that the absolute value of a number is less than or equal to m is equivalent to saying that that number has to be in between negative m and positive m on the number line. So what this means is that in terms of our sequence, every element of this bounded sequence lies in between here on my number line. Of course, we have another way to describe this using our two-dimensional thing here. So if we think about our index as being plotted on this horizontal axis and the value corresponding to that index is plotted on the vertical axis, this says that the entire sequence has to occur in between these two. So the key quantifier here is the for all n. So that means that a sequence is bounded if you can find an m so that every single one of these pieces, these elements in the sequence, are still in between here. Now, they may actually reach up and touch that level. Okay, that's allowed, but they cannot go outside. So if you found a sequence element that's outside of those bounds, then your proposed bound for the sequence is invalid. So some sequences, as we've seen, are bounded and others of them are unbounded. And we have a couple of different examples of those that we can take a look at. But the notion of bounded is, like we said, in terms of real numbers, gives me about this in terms of the sets of real numbers, tells me that this is setting inside of negative m to m, kind of capping it from both directions. So both from the right and from the left, or if you're more vertically oriented, from the top and from the bottom. So from both sides, I'm limited here. We can relax our vocabulary a little bit to talk about boundedness on only one side versus another. So instead of talking about bounded as a general description of a sequence, we can also discuss the idea of bounded above versus bounded below. And this definition of bounded above and bounded below should match our understanding of what the sets are, our understanding from what the definitions are in terms of sets of real numbers. So, for example, we said that a subset is bounded above if you can find, if for all x in A, that x is less than or equal to m. Okay? Well, this idea here still coincides with our notion of a sequence. It's just that now we're saying that the set A is the set of all n, or all a sub n, where n is a natural number. In that setting, in that sense, this idea of bounded above and bounded below can apply to sequences. And we can also talk about supremum and infimum in this sense. So not every sequence is bounded in any way. Some sequences are, so if I think about this way, the sequence -1 to the n, that's a bounded sequence because it just bounces between -1 and +1 for all forever. Okay. The sequence a sub n is equal to 1 over n squared. So these are reciprocals of 1, 1/4, 1/9, 1/16, etc. This is a sequence that is also bounded, but we can say that it's bounded above by 1 and bounded below by 0. All right, so in this particular example, our bounded m has to be 1. Because otherwise anything bigger or smaller than that will skip a sub 1. So but 1 is just the upper bound. There's a lower bound that's closer to the rest of the elements here, and that would be 0. So we can use descriptions of bounded above and below to narrow in a little bit more specifically what's going on with the sequence. And there are some that are bounded below. So a sub n is equal to n cubed. This is an example of a sequence that's bounded below by 0, but it is not bounded above because, as you notice, each n gives me larger and larger values in my sequence. And in fact, if you think about the function y equals x cubed, that's the graph, that's the picture of the sequence, or subset of that is the sequence that we're discussing here. So that's one example, but there's also examples of sequences that are neither. A sub n is equal to -1 to the n times n. So this starts out at +1, goes to -2, goes to -1, +2, -3, +4, and so forth. So you see that it's growing in both directions. So this would be an example of a sequence that is not bounded in any sense of the word. So this language of bounded should correspond to the ideas that we have from subsets of the real line, but in this context we can be more specific with our sequences.